Well, good morning or afternoon if you are in chemistry today. We're talking notes on empirical and molecular formulas. And by the way, these are still a part of your notes 5.5 that you've been taking on really fancy high-tech notebook paper. And this is going to wrap it up for those notes, which means we're coming up on a unit test here pretty soon. So you should consider this your 1 week morning for a unit 5 test. But anyways, 5.5 continued here on your notebook paper, and that should do it. Talking about empirical and molecular formulas. So here we go. First of all, we have been talking about empirical formulas, and we've been doing that through the percent composition if we don't have mass data. So just as a reminder, the empirical formula of a chemical compound is a representation of the simplest mole ratio between the elements that make it up. So when I see something like water, H2O, that means I have 2 moles of hydrogen for every 1 mole of oxygen, and you can't simplify that any further. A 2-to-1 ratio is not simplifiable. So that is an empirical formula. Today we're going to compare that to what's known as the molecular formula. And the molecular formula of a compound is not necessarily the simplest mole ratio, but the actual mole ratio. So the molecular formula of a chemical compound is a representation of the actual mole ratio between the elements that make up the compound. And so for example here, you guys learned in biology that glucose is a very important biological compound in synthesizing ATP. So glucose is actually C6H12O6. And that is because there are actually 6 atoms of carbon in the compound, 12 atoms of hydrogen, and 6 of oxygen. But that can be simplified. That is not the simplest whole number ratio. So we would call this the molecular formula because that's what's actually there. If I were to make this out of Tinker Toys, I would count 6 black carbons, 12 yellow hydrogens, and 6 red oxygens. But you can simplify this. The ratio 6 to 12 to 6 can be simplified if you divide everything by 6 to 1 to 2 to 1. And of course in chemistry we don't really write 1, so that'd be just CH2O. So that would be the empirical formula of glucose. So the empirical formula of glucose is just the most simplified mole ratio, whereas the molecular formula is the actual formula, like what is actually there. So as another example, if you take water, if you were to build a molecule of water, you would have 2 H's and 1 O. So that would be the molecular formula. But if you try to simplify that, you can't. The simplest it gets is H2O. So that would also be its empirical formula. So it is possible for those two things to be the same, but sometimes the molecular formula is a multiple of the empirical formula. It's kind of like if you were to take a test and get 80%, let's say. So let's say you take a test and you get an 80%. So that might mean you got an 8 out of 10. Or that might mean you got 80 out of 100. Both of those equal 80%. In fact, if you got a 4 out of 5, that'd be 80%. If you got a 20 out of 25, that'd be 80%. So all of those things have the same ratio of questions that you got right to questions you got wrong. But which one did you actually take? Well, if it was like a homework, it'd probably be like a 20 out of 25. So the empirical formula would be the 8 out of 10 in this case, or the 4 out of 5, I guess, because that's the most simplified. But you might have taken a 20 out of 25 as the actual number of questions or points that you could have gotten. So let's take that information and let's do an example. So what this means is that the ratio is the same, but the molecular formula is a multiple of the empirical formula. So I have an example here. It's about caffeine. And I've got a percent composition here. So it says caffeine is 49.48% carbon, 5.190% hydrogen, 16.47% oxygen, and 28.85% nitrogen. If its molar mass is 194.19 grams per mole, what is its chemical formula? And I have some steps here for you to work this out. So write these down and then we'll do them. Number one, we're going to find the empirical formula. So notice we have some percents. So we're going to assume we have 100 grams and change those to grams and find the empirical formula. We're going to find the molar mass of the empirical formula. We're going to see how many times bigger the molar mass of the molecular formula is. And we're going to multiply all subscripts in the empirical formula by this number. So here we go. Step one, find the empirical formula. So we're going to start with our carbon. We have 49.48 grams of carbon. And for every 1 mole of carbon, that would take 12.01 grams of carbon. If I divide 49.48 by 12.01, I'm going to get 4.123 moles of carbon. Remember, I'm getting the mole ratio to get the empirical formula. So I'm just finding the number of moles and comparing the ratio. So for H, I've got 5.190 grams, and for every 1 mole of H, I have 1.01 grams of H. And if I divide 5.190 by 1.01, I'm going to get 5.190. Keep going. I have 16.47 grams of oxygen, and it takes 16.00 grams of oxygen to make 1 mole. And so I'm going to get 1.029 moles of oxygen. And then last but not least, I've got my nitrogen, 28.85 grams of nitrogen. And nitrogen has a molar mass of 14.01 grams per 1 mole. And that comes out to be about 2.061 moles of nitrogen. So now that I know the number of moles of everything, remember I want to find the mole ratio, which means I need to divide all of the moles by the smallest number of moles. And what that's going to do is make this one a 1. So oxygen is going to be a 1. Now if I divide C by that number, I'm going to get almost exactly 4. So if I divide that by 1.029, if I divide 5 by that number, I'm going to get almost exactly 5. And if I divide nitrogens by that number, I'm going to get almost exactly 2. So my ratio is 4 carbons, which would be C4, to 5 hydrogens, H5, 1 oxygen, O, and 2 nitrogens, N2. So that's step 1, and that is the most work. So next what I'm going to do is find the molar mass, it says, of my empirical formula. So you do that just like you would any molar mass by adding up all of the molar masses of the elements and getting a total. So to do that, I'm going to take carbon, which is 4 of them, times 12.01, plus hydrogen, 5 of them, 1.01, plus oxygen, 1 of them, 16.00, plus nitrogen, 2 of them, 14.01. And when I do that, I get a molar mass of 97.0 grams per mole. So that's the molar mass. Now, step 3 is where it gets interesting. It says, see how many times bigger the molar mass of the molecular formula is. And that's always given to you in the problem. So the problem says if its molar mass is 194.19. And so our molar mass is not 194.19. It's some amount smaller than that. So we need to see how many times bigger is the real formula than the empirical formula. So we're just going to divide the two. So if we take 194.19 and we divide it by 97.0, we are going to get a number that is pretty much spot on 2. All that means is that the molecular formula is twice as big as the empirical formula here. So we're going to take this, we're going to keep the ratio the same, and we're just going to multiply everything by 2. That way it's still a 4 to 5 to 1 to 2 ratio. It's just that there's actually twice as many of everything, which means that our final answer, our molecular formula, is C8 H10 O2 and N4. So that would be your molecular formula. So notice if you divided all those numbers by 2, if you tried to reduce, you get your empirical formula again. But caffeine's actual formula is C8 H10 O2 N4. So what I'd like for you to do today is I'm going to give you a boat ton of practice problems that are regarding percent composition, which remember is finding these numbers. We did that last week on Thursday. Empirical formulas, which we did last week on Friday. And now molecular formulas, which kind of makes you do all 3 essentially. And so I want you to just work your way through those and do as many as you can. Please remember that your pre-lab questions from yesterday are going to be due tomorrow. If you don't have those done, you will not be doing the lab. I really, really, really want you guys to be able to do the lab. So please make sure those pre-lab questions are done when you walk into class tomorrow, like very first thing right off the bat. Okay, that's it for me. Have a wonderful rest of your day, and I will see you soon. Bye.